So hello everyone. In this video, we are going to discuss the second identity, the sum of rows in Pascal's triangle. So you are already familiar with the Pascal's triangle and how it is related with computing the binomial coefficient. So for example, if we have x plus y quantity squared, so it will be expanded to x squared plus 2xy plus y squared, correct? And for each term, we have the coefficients 1, 2, and 1. So, and then for this row, which is linked to x plus y, quantity raised to 3, so that the coefficients would be 1, 3, 3, and 1, and so on. And we have already discussed in the previous video that let's say we have this 2, and it may be computed from, or it is actually the sum of its adjacent sides. Okay, so now we have another identity, the sum of rows. So the first row, the sum of this row is 1. The sum of this row is 2. So 1 plus 1 is 2. The sum of this third row is 1 plus 2 plus 1 equals 4, and so forth. Okay, and we see a pattern here. This 1 is actually equivalent to 2 raised to 0. This 2 is equal to 2 raised to 1. The 4 is equal to 2 raised to 2, and so on. Okay, so we can then generalize that the sum of a certain row is equal to 2 raised to n. Okay, so how did we arrive to that? So for example, we have on the this row where n is equal to 7. So this value may be computed from n taken 0, right? Then this 7 may be taken from 7 taken 1, 21 from 7 taken 2, 7 taken 3, 7 taken 4, until 7 taken 7. Okay, so we can then say that the sum of a certain row, n taken 0, until n taken n is equal to 2 raised to n. Okay, so if we have 7, let's say n is 7, so that would be 7 taken 0, and the sum of 7 taken 0 until 7 taken 7, and that would be equivalent to 2 raised to 7. Okay, so let's have the proof, and I'll just transfer to a separate device. Okay, so let's go back to the proof. So how can we prove this previous statement? Our identity is this, and we want to prove it. So again, let us consider this set as containing 1, 2, 3 until n. Okay, so we are going to count the total number of subsets of S in two different ways. So if we have a set S, so how many possible subsets can we have? So first, what we can do is to count the number of subsets with no elements. So meaning we have an S, right? And then 1, 2, until n. So meaning this first na set does not have any subset. It does not have any element. So that may be computed with n taken 0. And the number of subsets with one element. So that would be, let's say we have only 1, or we could have only 2, and we could have only 3, and so on. Okay, so one element lang siya. How about for the number of subsets with 2 elements? So it could be 1 and 2, or 1 and 3, and 1 and 4, and so on. Okay, how about for number of subsets with n minus 1 elements, meaning we only one element of the original set is not included in the subset. Okay, and the number of subsets with n elements, that is n taken n, So we want to count the total number of subsets that we have. And then the number of subsets with no elements is n taken 0. The number of subsets with one element is n taken 1. The number of subsets with two elements is n taken 2, and so on. Okay. And what about for the second way of counting the subsets of S? So when we are building a subset of S, there are two choices for each element. Either it is in the subset or not. So for instance, again, if we have a set S and it contains 1, 2, 3, 4 until n, so what would be, and then we are building a subset. Let's say subset of S. And so would 1 be included? Yes or no? So that would be, there are two possible ways. Okay, so there are two possible ways. Is 1 included? Wait lang. We have a yes or no here. This could be either yes or no. And then this would be yes or no. Or yes or no. Then this would be yes or also no, etc. Okay, so there are, for each of the element, there are, it could either be chosen as to be included in the subset or not. So we can then say that there are 2 raised to n ways to build a subset. And so we have the first way and the second way, and then we can prove that they are equivalent.